Welcome everybody to RISE Learning Machines seminars. I am Olof Mogren. I'm a researcher here at RISE, which is Sweden's public research institute. And this is our open weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working on AI to fight climate change. This meeting will be recorded. Let us know if you want to be removed from this recording. And check out the collection of great talks that we have collected on our YouTube channel. Today, I'm introducing Markus Pettersson, who's a PhD student at Chalmers University of Technology. Markus works at the intersection of machine learning and Earth observation, and focusing on poverty mapping and its applications in development research. Today, we'll talk about debiasing AI predictions for causal inference without fresh ground truth data. And with this said, I will hand over the word to you, Markus.
Thank you very much for the kind introduction. Let me see. Is the presentation visible, Remro?
Yes, looks good.
Yes, thank you. Right, yes, so thanks for the introduction. My name is Markus, and I'm going to present to you a work that we recently sent into AAAI, where we talks about, debiasing machine learning prediction for causal inference without additional ground truth data. And this will then hopefully allows us to progress towards our overarching goal that I will present a little bit further, that we call one map, many trials. So first for some background here with poverty measurements. So today there's about 700 million people in the world globally living in extreme poverty. And poverty researchers today have a sort of good idea of what the picture looks like on a national level, right? So we know which countries are wealthy, which countries are poor, which ones are trending in the right and the wrong direction. But for many applications, we would like to have some more local insights. So we would know, instead of which country is doing well, we want to know which villages are doing well, which neighborhoods in the city might have a stagnated development. And traditionally, this data has only been available through collection via surveys. So basically going house to house, door to door, knocking on and asking if you have access to running water, what kind of roofing material, and so on and so on. But as you can imagine, this is a very expensive process. And see if I can move it. Yes, this is a very expensive process. And poverty research, almost by definition, is a field which lacks access to funding. So there's a lot of large gaps in this data where we simply don't know for many local regions what the wealth level has been historically. So the way that we see this, and many other groups are similar working on this, is whether or not we can use satellites images and machine learning as a proxy in order to fill in these data gaps. And so the pipeline for this typically goes that we have some geotagged surveys where someone has gone out and asked these questions, and then also recorded a coordinate of the village where the survey is being conducted. And we then use the answers to these surveys to construct a wealth index for the material wealth, so basically the assets that the households have access to. We use something called the International Wealth Index, and we can think of it basically as the first principal component of some of the answers to the survey. And as I said, these surveys are also geotagged, so we then have a GPS location and a date for when these surveys were conducted. And so we then go out and collect corresponding satellite images to this. We tend to use the Landsat 5, 7, and 8 satellites, which have a rather coarse resolution, but the advantage that they go back, have a continuous track record all the way back to the 1980s, which allows us to look at historical patterns in poverty over time. And what we then do is, now when we have images and we have labels, it's a simple image regression task. So we train some type of image regression model, could be a vision transformer or a ResNet or something off the shelf. And then once we have a trained model, we would then run inference, download satellite images for all populated areas of the African continent, which is what we're focusing on today. And yeah, make predictions for each village in the continent, basically. Right. But yeah, what would these wealth maps actually be good for? What can you do with them? And as I see it, there are basically two main avenues that you can go down here. One of them is more of a profiling task. Basically, you're interested in figuring out like where are the most vulnerable populations right now. For example, there's been this work here by Emily Aiken and et al., where they helped the government in Togo to where to basically decide where to allocate some extra aid money during COVID-19 crisis. So yeah, basically a geographical task of figuring out which areas are in dire need of assistance. But then there's the other branch that we are going to focus on a bit more today, which has more to do with causal assessments. So basically, can we use these maps to analyze some causal events? For example, figuring out what's the effect of some intervention. And as an example here, there's this paper by Rettelschall from a couple of years ago, where they used the machine learning model and satellite images, as I described before, in order to build out this wealth map of Uganda. And then they basically compared wealth maps over time with the expansion of the electrical grid to figure out what was the effect of a village getting access to the electrical grid on their levels of poverty, basically. Right. But yeah, so as I said up top, our goal for what we want to do with this map is a framework that we had chosen to call One Map, Many Trials. And the basic outline of this is basically what I described to you here before, that we start out by training some prediction model, and we then gather images for the whole continent and make some poverty map of the whole region. But then the end goal here is for us to basically be able to hand over this map to other research teams working with less of the machine learning side and more on the social sciences side, in order to evaluate their own interventions, basically. So the goal for us is to produce some type of map and some guidance on how to use this map, then hand it over to someone that we might not even have actual conversations with, for them to be able to then collect from using their own locations, treatment statuses, and confounders, and so on, be able to get the wealth information from our map and then run their own causal analysis on this map, on these values. Right. As you can imagine, this sort of setup comes with a lot of challenges, especially in regards to the bias that could be added here, right? And so these maps can be biased in a lot of different ways. It might come from simply the design of the surveys and the wealth indices. So basically, different cultures value things differently, right? So what might be considered a necessity in one country might not be even considered a luxury in another, right? So it's very hard to construct a single number boiling down all of poverty, or in this case, asset wealth, into a single index, which might lead to some type of bias here. There's also some sampling bias in how these surveys are collected. So the surveys that we are using are from the DHS program, which is a program run by the US government, which then naturally collects this data mostly for American allies. There's also the fact that they don't want to send out their surveyors into, for example, active war zones, meaning that people living in these situations won't be included in the surveys, therefore won't be included in the training data, and therefore will probably affect what the bias of our model and subsequent maps will then end up being. There's also a smaller part of this that's just satellite data availability. Basically, we have to filter out some of these locations just because there's no satellite images available for them, especially when we go back and look at historical locations from the 1990s, for example, when satellite data coverage wasn't as good. And there are many, many more versions of this, that, as you can imagine. But for this work, we want to focus on something that is very specific to the use of machine learning in this setting, and that is something that we call shrinkage here. So yes, what's shrinkage here in regression analysis? Well, basically, what ends up happening when you train one of these models, regression models, is that you will notice that the distribution of the predictions will have a lower variance than the observed original ground truth data. And what this means is that we will end up having a relationship between the observed wealth status and the residual of our predictions. So basically, for very poor locations, we are likely to overestimate overestimate the wealth levels, whereas for very wealthy locations, we are likely to underestimate the wealth levels, right? So we're sort of regressing towards the mean. And yeah, this is kind of interesting phenomena, and it's not due to something like squaring the residuals when we're training our model with minimum squared error, and it's not due to adding some type of regularization to our model, although those things can exacerbate the problem. So yeah, where does this phenomena come from? And yeah, I found an analogy for this that I really liked from a paper by Efron and Maris from 1970s, which links this to something called Stein's paradox. And so, yeah, what is Stein's paradox? Well, the example they use concerns baseball, and I'm not super familiar with baseball. I'm too European for that. But yeah, they have this one statistics in baseball called batting averages, which is basically how many times do you hit the ball divided by how many times do you get the ball thrown at you, right? As we can imagine here a setting where we have access to data for three different players. Red, who has, during his last three games, have had rather low batting averages. This blue player, which is somewhere in the middle, and this green player who have had very high batting averages. And the question then is, what will the batting average for each of these three players be in the fourth game? And a very tempting answer to this is to simply look at the conditional means, right? Like we take the mean of the three last games for the red player, the blue player, and the green player, and we give that as an answer for them. But what Stein's paradox tells us is that this might not be the optimal, or this won't be the optimal answer for this question that minimizes the residuals. And the reason for this is that we need to consider actually the distribution of our underlying labels. So if we look at all the games throughout the league season, we can see here that green has had some of the absolute best games of the season, right? And red here has been somewhat worst, and blue is somewhere in the middle. And right, so why has green had some of the best games of the season? And there's two parts to this, right? Like the one is that green is probably a very good baseball player. Like he is very talented and good at what he's doing. So therefore he's going to have higher batting average than what red and blue is going to have. But it's also very likely that at least some of this comes from him just being lucky, right? Or unobserved variables. Like, for example, maybe the green player has faced easier opponents in the last three games. And now for the fourth game, he's more likely to face an average team again, right? So what Stein's paradox tells us is that we are better off, in order to minimize residuals as much as possible. We shouldn't just take the conditional mean for each player, but we should actually consider the shape of the entire distribution and pull our predictions a little bit regress towards the mean, right? So as long as there is any uncertainty, if we have a complete set of information, like we knew everything about the game for green, then there's no need to do this. But as long as there is some amount of luck or uncertainty involved, then we would need to regress our predictions a little bit towards the mean. And we can think of this as, if we swap out the last three games and batting averages for satellite images, we can think of this as having like a satellite image of a village that looks very wealthy. Like it looks like it might be the wealthiest village in Africa from all we have. But as long as there is some uncertainty, it's better for us to hedge our bets, or for the model to hedge its bets and regress the prediction a little bit closer towards the mean, since it's very unlikely to observe this type of value otherwise, right? And yes, and this is not using any form of Bayesian models or anything like this, right? Like this is just in order to minimize the size of the residuals. So this is a standard MSE training exercise, right? Which is kind of interesting. And this is where the source of this attenuation bias comes from. And I should say that this is also a sort of a simplified argument here, because we wouldn't actually be pulled towards the mean, but rather we would be pulled towards the closest mode. So we can imagine some type of bimodal distribution, right? Like, for example, with the baseball players here, maybe there's the female and male players in the data set, and female players for some reason have a higher batting average. Then if we're close to the female peak, we're likelier to be pulled towards that peak instead of towards the mean of the two modes, right? And this is actually what we see in our poverty data as well, where we would have one mode for rural clusters and another mode for the slightly wealthier urban locations, and same likewise with different countries and so on and so on. Right. I forgot to say, but feel free to ask questions and interrupt during my presentations if you have any questions. Otherwise, we can take it towards the end. But feel free to interrupt at any points. Right. So how does this then affect our causal estimates? Well, if there is a positive treatment effect, so yeah, let's give this example here where we have some type of treatment where there is a positive effect on the village. I have some simulated data over here where we have the treated locations generally being wealthier than the controlled ones, right? And we will fit the model same way as always. What we then end up seeing here is that the treated wealthier locations are more likely to be underestimated, and the poorer control locations are likely to be overestimated. And so when a village then is treated, it goes from being likely to be overestimated to being more likely to be underestimated. And if we imagine this relationship as linear, so we imagine that this distribution here follows the linear relationship where our prediction is some linearly scaled version of the true observed value. Then we will have, in an RCT setting, we will have an average treatment effect, the difference between the treated and the control groups. That is a scaled version of the true underlying treatment effects.
Short question.
Yes, please go ahead.
Treated here means that a village has electricity.
Right. So, for example, it's good that you pointed this out. What we want to do is we want to be able to do this for many different types of treatments. Like we don't know what the treatment is beforehand. And so here it's just some simulation where we have ourselves decided that some locations are treated, whereas others are not, and we have increased their wealth because of this. But we can imagine that, yes, it would be access to electricity. It could be, as we will see later, like some interventions by the World Bank or the Chinese governments where you have built some infrastructure or, handed out school supplies, run some vaccination program, or, basically anything you can think of at the moment. But yes, good point. Does that answer your question?
Yeah, thank you.
Right. Right. And so what we see here in our simulated setup then is that when we rerun the experiment many times with a larger and larger treatment effects, basically we move points further and further to the right, depending on if they're controlled or treated, we will see an attenuation effect here where we underestimate the magnitude of the treatment effects. Like for treatments where the effect was negative, we won't have as negative as the true value. And for for treatment effects where we have some positive effects, we won't capture the full extent of those positive effects, basically. Right. So how can we correct for this? Well, we have come up with two different versions of this. And the first one is very, very simple. So same as before, we assume that there's a linear relationship between the predicted and observed wealth. Then we simply estimate the slope of this relationship. And as we saw before, in this setting, the estimated treatment effect will just be a scaled version of the true treatment effect. And we can estimate this parameter k on a holdout data set. And then we will have given that these linear relationship holds, we would then have a unbiased estimator of the true treatment effect by simply dividing our estimated treatment effect by this estimated k value here. Right, so that's the simple linear setting. But yeah, is there something more interesting we can do? And that's when we come to discovered something from the way I found about it is through the literature on Gaussian diffusion models. So it's this thing called Tweedy's formula, which shows up in a bunch of different places. But basically, it's a way of explaining the relationship between these two quantities if we model the true outcome as a probabilistic version of the predicted outcome. So if we have our model predictions y hat, then we model that the true prediction or the true underlying wealth will fall somewhere along this Gaussian relationship here, where we have some type of noise relating to how uncertain our prediction is, but then centered on our predicted value. And what we find here from Tweedy's formula then is that basically the predicted value given the true value will just be the true value, but then nudged somewhat in the direction of the gradient of the probability distribution, as we saw before. So basically, if we think about the nice bell curve with batting averages, then we will be nudged towards the center. And the size of this nudge will be decided by this sigma square parameter, which is basically how uncertain our model predictions are for each point. Right. Yes. Right. So now we have a relationship from the true value to what our prediction is likely to be. But how does this help us with finding out a way to correct for our faulty predicted treatment effects? So if we take this and see what will then our average treatment effect estimate be with our predicted labels, we can see plugging this value or this formula into our formula for the average treatment effect. We can see then that the estimated value for our treatment effect estimate will be the true treatment effect plus this scaling factor here that comes from the differences in the mean gradient slope of the treated set and the control set. But yeah, this formula still contains some values that we won't have access to, like we won't have access to what the true treatment effect is, right? So is there a way to use this to get an unbiased estimator for the true treatment effect? And using the fact that this term here can be substituted for an estimated the expected value of the gradient on not the probabilistic or the distribution of the true labels, but of the predicted labels instead. We can plug this into our formula up here, throw some stuff around, and then end up with an unbiased estimator of the true treatment effect, given that our homoscedastic assumption above holds of how the relationship between y and y hat, which follows this Gaussian curve.
Question.
Yes.
How come you can do that replacement? I didn't follow that.
Yeah, exactly. So it's a good question. It's how can it's a bit involved, the derivation of this. Yeah. But
Okay, it's a
yeah,
discussion for another time. But
I think it might be. Yeah,
but if
I
we
will
go into
refer
the
you
paper and
to
read it, then we'll see that you can do this.
exactly. I think I will refer you to the appendix. So yeah, if you're willing to take my word for it now, then I hope it's okay.
Yeah, I think that's good.
Nice. Okay. Right. So now we have an unbiased estimator for what the treatment effect would be. Uh, so uh, yes, and these values here, right? The the gradient of the predicted labels and the uncertainty scalar here, sigma squared, is something that we can estimate, right, from our data. So we estimate these values using a held out calibration set. And therefore we have now functions in order to turn our attenuation biased tau hat into an unbiased estimator of tau. Right. So some result on this. If we remember from before, what I said was that we overestimate poorer regions and underestimate wealthier regions naively. And so as a build up towards the causal results here, we started out with actually putting this to the test to see whether or not we could correct for this attenuation bias. And sure enough, so what we have done here is basically we have grouped the locations in our surveys by admin level 1 regions, which would be roughly equivalent to states in some countries or provinces in other. I guess in Sweden it would be regioner. And then we have calculated the mean RWI value from our survey data for both the observed case, where we look at the labels of the surveys, and from our predicted case, where we look at our model predictions of these locations instead. And sure enough, in the naive case here, we do see some of this attenuation bias, where basically we overestimate the wealth for poorer regions and underestimate the wealth for wealthier regions. Or I guess here in this case, it's more, since all the values are positive, it's more that we are underestimating for the wealthier here. And then, yeah, when we apply our first simple linear correction adjustments, where we simply calculated the value k hat and divided our predictions by this, we can see that yeah, we are overcorrecting this attenuation bias, so we get the bias in the opposite direction, and this is likely because the true relationship between y and y hat isn't actually linear as we might have hoped for. But when we instead turn towards our Tweedy adjusted sets, as we described here above, we can see that we essentially get rid of this attenuation bias estimate. And even though this is still involves us estimating some more parameters and stuff like that, adding another source of variance to our estimates, we can still see that the mean average error in general goes down for these aggregated estimates. And sure enough, if we then also take a more geographical approach to this, and we look at doing the same thing, but for admin level 2, so basically equivalent to commune in Sweden, or yeah, the next administrative level below states and provinces, I guess. And we look at where does this Tweedy correction increase or decrease the predicted value. And we see that these map pretty much align very well in places where we before overestimated the wealth, we now correct downwards. So we push it down towards being unbiased again. And yeah, so as you can see, this seems to hold up to some extent if we look at the geographical perspective as well. Right, but as I said, at the end of the day, we want to do this not in a profiling task, but some type of causal interventions. So yeah, we would like to evaluate how well does this approach work for capturing the true treatment effect of some interventions. And there are some issues with this, namely that it's very rare to have actually known treatment effects for these kinds of settings, right? Like it's hard to say what is the true effect of poverty in a village from some type of intervention. But we think we have found a clever way to get around this in order to actually still evaluate our model on real interventions out in the wild. And so we start out with this geotag data set we have with interventions from the World Bank and the Chinese government. So basically, each one of the dots here on the map is some type of intervention. These interventions are then grouped by different aid sectors. So we can see that some of these will be related to health. So it could be vaccine programs. It could be building of a hospital. There's multiple different types of intervention goes into this overarching aid sector idea. And what we end up doing here is, right, so even though we now have a data set with aid interventions that we can look at, the treatment effect of these interventions are still unknown. So yeah, how can we still use this data set to evaluate our model with? And the way we have gone about doing this is that we split this DHS survey data that we were working with into upstream and the downstream data sets by randomly sampling. And we then train a model, do the calibration and all the model preparation stuff on the upstream data, as we call it, without any knowledge of what type of trials or interventions that we want to study in the next step. And then for the downstream data, where we held out some of the survey data, we then start by selecting an aid sector from the other intervention data sets. So for example, all the health projects by the World Bank in our intervention data set here. And we find locations for all of these. So we locate all the admin level 2 regions, which has some type of health project intervention within them. And then we look in our held out downstream survey data sets for villages within these regions that were surveyed between 3 to 8 years after these interventions took place. It's not a perfect science here, but I'll get into why this is still an interesting comparison later. And then we simply consider the villages that happen to be within the same admin 2 level or admin 2 region as the interventions as treated, and then we take the villages survey that were not in these admin level 2 regions from the same time as control sets. Right, and so now we have a way of actually getting a true treatment effect by using the values from the survey, right? And similarly, we make predictions for these downstream locations with our model in order to get a predicted treatment effect as well. Right, exactly. So we estimate the treatment effect both using the survey values that we have recorded in our survey from these locations and the predicted values from our model instead. And what we can see here is very similar to what we saw on the previous slide here. We can see that the naive model, where we just use the model predictions as they are without any form of attenuation bias corrections, we do see some of this attenuation bias still, where we have a slope here that is below 1, basically. We tend to underestimate the effect of products that work very well. Right, and when we do this simple linear correction, we tend to overcorrect, suggesting that this linear correction is not very well suited, and showing that this data, the relationship between y and y hat might not be too linear after all. But when we run with our then like the Tweedy model or MSD predictions with our Tweedy correction, we can see that again our attenuation bias is basically eradicated. And because of this, similarly, we also end up with a lower mean average error. Right. And so yes, so it wouldn't be fair to give this presentation without giving some other options as well for how you would be able to do this type of bias correction. And something that's very popular in the literature now is this whole field with prediction-powered inference, where you basically having a held out calibration set, you can estimate what the residuals would be and then get some nice statistical properties on a guaranteed unbiasedness for these interventions. I'm not going to go too deep into detail on how this method is calculated, but if this is something that some of you have come across before, it might be a logical comparison to give here. And as we see, when we use this prediction-powered inference method with keeping basically revealing the labels of 10% of this downstream data, we managed to also get rid of this attenuation bias effect and get a lower mean average effect or a mean average error. But yes, as I said, this then requires us to reveal this additional label data from the downstream, because what prediction-powered inference requires is that we require some fresh labels, and not only that, we also requires labels that have both the target values of wealth and the treatment status at the same time. So we would need to have survey locations basically where we both know that the treatment status of the village and the wealth of the location, which, if you remember from before, our idea of this one map, many trials, basically building one map for poverty that you can then use to evaluate against multiple different downstream tasks. This is not feasible with that. Like, you would need to have the downstream team would need to collect some new data on wealth for them to be able to get these unbiased predictions. And we also ran some experiments with how much of this downstream data set do you need to reveal to this prediction-powered inference method for it to reach the same predictive performance as our Tweety-corrected predictions. And of course, this will depend on different tasks and data set sizes and so on and so on. But in our setting here, we found that you would need to reveal the true label of at least a third of the downstream data set in order to reach comparable performance as the Tweety-corrected predictions. Right. But yes, so as I said, like these interventions that we looked at here, it might not be the most interesting in the sense that we are grouping all types of health projects, for example, carried out by the World Bank together into one big lump. It doesn't matter if it was handing out Band-Aids or if it was building a new hospital, right? Our method only shows that the average treatment effect of a World Bank intervention is this much. But we tried to do a little bit more, where we also adjusted for some basic confounders. So here we adjusted for country, year, and whether the location was urban or rural. And as we can see here, we then still retain this unbiasedness property. We don't have as nicely a reduction in the mean average error as well as before, but part of this comes down to how this analysis is carried out, right? Because in order to get a fair comparison here, we only made inference predictions for the locations where we actually had survey data, right? And due to this Tweety correction and so on, involving estimating more parameters, this will naturally introduce some added variance. But the nice thing about this variance is that it's variance and it's not bias. So if we then now are able to sample more and more locations, we can get the bigger and bigger n, right, to divide by. So the variance of the mean predictions, which is basically what we are looking for when we are interested in treatment effects, right? It's the average treatment effect. The variance of those will shrink as we get access to more and more villages, and the whole basis for doing this these maps, right, is to get access to more of these labels. So we make predictions for each village in the region instead of just the two where we happen to have surveyed samples from. And yes, what we found here in this intervention, as you see, it seems that that some of these Chinese interventions, which might be like up here, I believe it was some type of integrating more women into the workforce, that this would then increase, according to this rudimentary study here, would increase the wealth level with 20 points on a scale from 0 to 100, with how much material wealth a village has. And as we can imagine, this is likely not due to the actual effect of these interventions, but more likely due to us not adjusting for more confounders and so on. So this is in no way a watertight analysis in order to get the actual effect of these interventions. But that's not really the point that we're trying to make here, because the point that we're trying to make is that we will now make the same mistakes when we used our predicted maps. So when we use our predicted values as we would when we use our observed data from the survey, right? So the point is not to make as good of a prediction as possible. It's just that we will make the same mistakes with our predicted map as we would do with our surveyed survey data set, basically. Right. But yeah, as you can imagine, this work still has some limitations for what we can do. So first off, perhaps the biggest one is that this whole story that I've been telling with attenuation bias is far from the full pictures. There are, of course, many other types of bias. I mentioned some of them up top that might still affect these interventions here. Most of the comparisons we've been doing here has been on some assumed RCTs, so randomized controlled trials, where every village on the continent is equally likely to receive some type of treatment, which is obviously not the case. These interventions are selected very carefully for which regions they should be implemented in. So there's a lot more work to be done there with where this is sound from a causal analysis perspective. In addition to that, we still haven't addressed any of the problems with doing this with multiple measurements over time. So if you want to do something like a difference analysis, for example, where you make a wealth map for each year and you track the development of a village over time, it's unclear at the moment yet how to adapt this framework for something like that, as it's very unlikely that the measurement error for the year 2008 of the village and the year 2009 of the same village, it's very unlikely that the measurement error of those two will be unrelated to each other. It's very likely that we have overestimated in both cases, for example. And the third point I want to address here is that we are still making some rather weird assumptions with this for the treatise correction. For example, with the homoscedasticity, that our model is equally likely to make equally big mistakes or for two villages with the same IWI score. And this is probably not the case. Like it's very likely that the model should be able to make more accurate prediction in some regions than in others, depending on where we have a lot of data and so on and so on. There are some version of treatise formula out there that can deal with some types of heteroscedasticity. So this is something that we want to look into further into the future for how we can perhaps adopt this framework for some more advanced and more accurate assumption of what the modeling error looks like. Right. With that being said, I encourage you all to go and check out our preprints. That's, yeah, as I said, we submitted this to AAAI about a month ago. And yeah, I'd be very, very interested to hear any feedback or any thoughts on what you might think about this work and what we have done there. In addition to this, I would also encourage you guys to go and check out our lab website where we have a lot of cool visualizations and stuff like this. That's very fun to play around with. Basically, yeah, studying what these model predictions look like for different locations on a continent, and make some comparison about where the wealthiest regions are and which ways they are trending and so on. Right. So thank you very much. Do we have any further questions for me at the moment?
Thank you, Markus. Super interesting stuff.
Thank you.
I'm sure we'll have tons of questions. And since I'm speaking at the moment, I'll just throw one out while people work up the courage. So the upstream and the downstream data that's divided by time. Is that right?
So in this case here, we actually didn't do a division by time. We have just sampled. So the way that we might see it in the future, let's see if we can go back up to. I guess we have to look. Yes. So if we go back to this overarching idea that we have up here, then we can say that the upstream data is it's everything that's going on in a model training prediction phase. So what we would ultimately want to do is to train our model on the full survey data sets and treat that all as upstream data. And then the downstream data would really in practice would then really only consist of the locations where some intervention has been made, the treatment status, confounders, and so on and so on. And then you would sample the predictive wealth values from our map we have handed over here. In order to do some comparisons in the experiments that I talked about down here, we had to set aside some of the upstream data as part of the downstream in order to have something to compare to.
All right.
But yeah.
Thank you. And my real question is, you were talking a little bit about confounders, and have you looked into this? Have you studied it in any way? Have you sort of identified what kind of variables there are and what things do correlate with the kinds of interventions that you are looking at here?
Right. So I mean, there is. I haven't personally looked into this, but there is a lot of literature out there on what causes sort of these aid projects to be located in some regions and so on. There's a lot of interesting stuff out there with like the home region of the head of government is much more likely to be given international aid than the other regions of the country, for example, and all these other more geopolitical interest rates. There is some, we are basically starting out now with some more trying to formalize this a little bit more, like what type of confounding can we handle? When is this like analysis still causally valid? I think basically the only thing that we have come to a conclusion for so far is that if the treatment itself is visible in the satellite image, then that seems to implement some of the noise here. So I know we're not the first people to talk about this. I know the people here who made this paper with electrification here. In general, it's sort of common to include sort of nighttime light data when making these poverty maps, because there's a very clear correlation between having a lot of nighttime lights and having higher levels of wealth, right? But they couldn't include this here basically because that's also an indication that nighttime lights is also an indication that the village has access to electricity, right? So that would cause some issues with with the downstream analysis. But other than that, this is something that's obviously very, very crucial to getting this to work in a practical sense. So yeah, we are looking more into what type of if the confounders can the confounders appear in the image, for example, and so on, and this still be valid. So yeah, that's something that we're looking into. Does that answer your question?
Yeah. Yeah. Thank you.
Nice. Thanks.
Do we have some more questions for Markus? I have more questions.
Shoots.
Yeah. So about the data, you were talking about Landsat 578,
Hmm.
and for example, Sentinel-2 has at least higher resolution. I
Yeah.
think it also has shorter revisit times,
Yeah.
if
Exactly.
I'm right. But it doesn't have as long history, of course, as you mentioned.
Yeah. Exactly.
But have you or have anyone looked into sort of what would the difference be if we had such high resolution data? How good could these models become, and yeah,
Yeah.
that affect your analysis in this case?
Right, exactly. Yeah. So yeah, we've sort of looked at Landsat data for a longer time in the lab for this simple reason that it's been available for the full period of all these surveys when they have been conducted. But it is a great question, and there is actually another guy in the lab who is now looking into this, basically redo this analysis, but with using Sentinel-2 data and so on as well. We've also been trying to get access to some of these even fancier data sets with even higher resolution, right? That could be interesting because as you say, like Landsat have a very very poor spatial resolution by today's standards. Each pixel in the image is 30 by 30 meters on the ground, right? So it would be hard to tell what type of car someone has parked in their driveway, right? Like we're lucky to see if there is a house there to begin with. So much of what we end up seeing here when we analyze what type of features the model pick up on is more like roads and access to closeness to the ocean and built up areas and so on. So yeah, that's definitely something to look into further.
Hmm. Interesting.
Mm.
Do we have one last question for Markus? Otherwise, thank you, Markus, so much for this interesting talk. We'll meet again in 2 weeks' time, September 11th, and then we'll talk about generative domain adaptation and foundation models for robust Earth observation. And that will be by Georges Lebellière from the CNAM in France. And so welcome back, everybody, then.
That's very interesting. Thank you.
Thank you.
Bye.